Up. All conductors of the same circuit, the grounded conductor, the equipment ground, bonding conductor shall be contained within the same raceway or cable. They are allowed to be run in parallel if divided evenly, with the exception of service jumpers. Conductors of AC and DC circuits are permitted to occupy the same equipment, but when they do, the conductors shall all have the same insulation rated to the maximum circuit voltage applied to any conductor. So what that means is if you're going to put an AC and DC circuit together, that AC cabling may only have a 300 volt rating. It's designed for 240 volt circuits, a 300 volt rating, a thin plastic layer is all it needs. Solar is 600 volts, and the cable is rated up to 2000 volts if you're getting the top shelf PV wire. And so if you have a 600 volt application like a solar array sharing the same raceway as that 120 volt AC circuit or 240 volt AC service, in that case, that 240 volt cable needs to have a rating of 600 volts. And so that's where you can get into trouble trying to combine your circuits. Protection from physical damage. Hopefully we're understanding that you got to protect things from physical damage. You can bore holes through wood members. You can, if your conduit is not strong enough, like non-metallic conduit, and then you're required to have a certain clearance requirement, say between the roof, so that a contractor doesn't drive a nail into your conduit and into the wires. There's under the decking requirements and says, well, there's different rules on whether or not you can actually conceal raceways and cables and boxes, if you can actually hide them inside the rooftop or not. And there's some options, to reinforce the underside of the roof with, steel plates and stuff to prevent that from happening if needed. If you're dealing with cable that is number 4 cable or higher, you need to provide a fitting, like a bushing that puts a smooth surface on the edge of that conduit. Although that's a good idea to do anyway, because you don't want your sharper conduit edge biting into your wires anyway. You have to consider, is your wire run going to experience expansion and deflection, and put in structural joints accordingly. And some of that is, well, is this EMT conduit, if I'm doing a huge stretch up and then a 90-degree bend out, how is that conduit when it stretches and contracts? Is it going to be sliding up and down the fittings, or is it going to be trying to push them off the side of the wall? So there's a little bit of a design issue. You need design knowledge on where to locate the expansion fittings. So there are requirements for how deep underneath your trench can go. 22 feet under a road, 1.5 feet under homes or driveways, depending on how thick your concrete is. Under a building, you don't need to have some cover. Let's see. And so where do we protect our direct burial wires? When they emerge from grade, when they come out of the ground, when they come up from the ground to our inverter mounted on the wall of the house, when they, let's see. Can you splice or tap them without the use of splice boxes? Yeah, we saw that fitting earlier. Heat shrink tape and terminal and direct buried into the ground. let's see. Now, to accommodate earth movement, in addition to drip loops, you need to arrange your appliances so that when the earth shifts, your cables don't get pulled out of place, your conduit connectors don't get pulled out of place. So, a direct burial cable, the question is, well, what's more dangerous? Like to have a rigid conduit run that doesn't move in an earthen environment that gets heated and thawed on a regular basis, stretching that conduit, pulling on it, and if the conduit fails, what then? Then is there a sharp edge next to the cable jacket? Is that sharp edge biting into the cable jacket? Is water getting into the conduit and filling it up? Is heat, heating up that air? And then because the conduit provides additional insulation, that conduit's getting hotter and hotter? Or is it better to direct bury a cable and give it a robust jacket so that it's listed for direct burial? Maybe even give it a mineral insulated sheathing so that animals like moles and stuff don't chew on it. And then we just give it a little bit of slack at the end. So as the earth thaws and dethaws and thaws and dethaws, that wire has a little bit of wiggle room to move around. You still have to protect it, of course, wherever it leaves and exits the building. Okay, so ferrous metal equipment shall be suitably protected against corrosion inside and out, except at the thread at joints that should be coated with a conductive, corrosion-resistant compound. And then aluminum metal equipment shall be provided with supplemental corrosion protection. So, if you have certain metal joints and aluminum, if you're using aluminum cable, you have additional sprays to put on the terminal to prevent corrosion. Non-metallic equipment like PVC boxes or plastic boxes must be listed for exposure to sunlight, chemical exposure. A battery room would be a corrosive environment. So you can't always just put any plastic box up on the rooftop. We've seen our raceway sealing requirement for whenever you're passing into the building from the exterior, you need to seal the raceway. I'm doing a quiz right now, and I don't even know the answer to this. Is the inside of the conduit needs the same environmental rating as its outdoor environment. So when you have conduit transitioning from the outside to the inside with a seal right at the point of entry, is it considered, where does the dry environment begin? Does it begin at the first box? Or does it occur at the wall where the seal actually is? I don't know. It's kind of splitting hairs there. You need a seal whenever you go from cold to hot, hot to cold, inside to out, outside to in. You need to seal that air, prevent circulation. There are certain rules listed in code for your expansion fittings. All the metal parts have to be continuous. So we've seen... And then we see there's even spacing requirements on how much free conductor space you have to put in outlets and junctions and switch points, which I don't see in solar code. All right, so let's see where we're at here. A conduit box or body shall not be required for each splice, with removable covers such as wire arrays, multi-outlet assemblies, auxiliary gutters. The covers shall be accessible after installation. So you can use larger bodies and perform multiple splices. You don't just have to have one fitting, one box per every splice there. You can combine things. MI cable shall not be required for accessible fittings of straight through splices. So you might even be able to splice outside of a box, which could be useful in building integrated solar, where you just don't have a lot of space to hide the wiring system between the solar array and the decking, you know, the under the interior of the building. Let's see. Protection shall not be required when a fitting is used. Okay. So a box, conduit, or fitting in a raceway for open or concealed wiring. A box, conduit, body, or fitting having a separately bushed hole for each conductor shall be used whenever there's a change is made from in conduit to open wiring. So what that's saying is you will have entryways with conduit fittings that are for single conductor, and the hole might be a half-inch diameter. And let's say your conductors are a tenth of an inch diameter, and you have 3 or 4 of them. You may be tempted to take that fitting for the larger single conductor and put your 4 smaller conductors into that fitting. And you might ask yourself, is this really what I'm supposed to be doing? And the answer is no. You know, when you're transitioning from open wiring into conduit or vice versa, you know, you should be getting fittings where if you want to put 4 conductors into the conduit, it spaces those conductors out while providing some sealing for you. So it has a little plastic piece with 4 holes in it for your 4 wires. You know, that's the code compliant way. You know, if you're not doing it the code compliant way because you're going out to Home Depot and trying to buy what you think will fit in a do-it-yourself situation, you know, you need to go back and do it the code compliant way. But you know, you also need to make sure that you're not violating the sealing section. So some of these fittings that are a little more expensive might save you some money on balance of system material or help you do the project in a professional manner. Let's see. A bushing shall be permitted in lieu of a box where the conductors emerge from a raceway and terminate at equipment such as open switchboards, unenclosed control equipment, or similar equipment. So up on the rooftop, we have some equipment, our roof-mounted rapid shutdown box, our microinverters, our DC optimizers. And then we have our solar cable that is rated for open air exposure. And so that solar cable is often clipped or tie wrapped underneath the array to the racking system. There's often a channel built into the racking system that you can kind of shove the cable into and then put some clips down to hide it. And some racking companies do it better than others. But then you get to the edge of the roof and you still have these open cables. And let's say you've planned out a masterful internal wire run. And so you're going from your rapid shutdown box directly into the attic, and your inspector's making you put another switch right under the attic. So whatever, you're going to make it a breaker panel, and that'll provide you with the ability to service and maintain the array, you know, as needed in the future. And then out of that breaker panel, you'll run another conduit run down to the inverter, whatever, you know, a little bit more added expense, but you're moving on with your life. Okay, well, you have this awesome internal conduit run coming up out of the roof and landing on a roof-mounted box. But from that roof-mounted box, you still have this gap where you have open conductors. And so let's say you put a piece of EMT conduit or PVC conduit to sneak it up underneath the array. Well, then all you've done is kick the can down the road, and now you still have open conductors. And you're like, well, do I really just shove these things all into the PVC? And it says a bushing shall be permitted in lieu of a box where the conductors emerge from a raceway and terminate at equipment such as open switchboards, unenclosed control equipment, or similar equipment. So, you might want to give these two sections a closer read. But just be aware that there are fittings to space out the conductors. This looks like if the conductor is fully enclosed, like coming up and underneath a transformer box that kind of shelters the utility equipment. So you're going into an enclosed dry area that's protected, not just coming up from the roof or ground where there's squirrels and stuff. Why do we have spacing requirements for wires in a conductor? The answer is, well, electricity produces heat in our conductors, and if we put too many conductors in a raceway, not only do we not have enough space for the conductors to be installed and move around, but also there's less air and less airflow and more conductors in an enclosed environment, and it just heats up. Air is a pretty good insulator, and so if you have conduit in an EMT run, you could have everything in your array going along swimmingly, and there'd be some issue inside that conduit with that wires, and you don't even notice it until that EMT conduit starts to glow red and there's smoke coming out of your combiner box on the rooftop because your cable jackets are smoldering. And so your conduit sizing and your conductor sizing, your EMT selection is not just, do I have the space to fit it all in, but is what I'm using not going to heat up, or is it appropriately sized to manage the continuous and non-continuous loads? So raceways, other than busways or exposed raceways having removable covers, shall be installed complete between splicing points prior to the installation of the conductors. So before you start putting your cables into the raceways, you have to have your raceway installation complete. When required for utilization equipment, raceways can be installed initially without a terminating connection at the equipment. And so that's where, if you're trying to power up a site, for construction with a generator, you do not need to you do not need to have a permanent, you don't have to have a proper raceway for your on-site generators when you're building. Let's see. Metal raceways shall not be supported by welding unless designated to be. So you're not allowed to weld your raceways. Generally, you'll put your raceways up on those conduit support blocks we were seeing from yesterday. Boxes with insulating supports. Other approved means insulation wedges. I guess that's another term for them. And the spacing for vertical, this is another thing, is not just spacing for horizontal supports, which might be every 30 inches for service conductors, and then maybe up to 5 feet or so for non-service conductors. But there's also vertical spacing too, because when these cables hang over the side of a wall, that cable starts to get heavy. And so it's not a huge deal, though. Every 80 to 100 feet, depending on your cable size, you need additional support. So I had a project with a standing seam metal rooftop. So I thought, well, I want to run my conductors directly through the metal roof, because I didn't want to have an ugly, unsightly run. But the problem that I had, and let me see if I can get my drawing tool up here. Here's our roof cap for a standing seam metal rooftop. And then there's what's called a Z-purlin that kind of snaps into the roof cap. Actually, I think it goes the other way around. But, and then we have our so I think the Z-purlin gets somehow clamped onto the roof. And then here's our standing seam, and it gets clamped down here as well. And so we have a standing seam, we have our roof cap, and we have about a 1-inch spacing here where this Z-purlin is. And I wanted to run my wires from the top of the array here. I wanted to take my wires and run them straight through that Z-purlin and then down into the wall. And that way, you know, when rain runs off this roof cap, it goes over the edge and not into my conduit. It's the perfect spot. You know, if on that rain, if I had put my penetration further here instead of going up and over and having that be sheltered, you know, that rainwater running down the roof could collect around that penetration and that could leak. So am I allowed to do this? Well, this says, you know, I have a ferrous metal rooftop. It says where conductors carrying AC are installed in ferrous, they should be grouped together. So this really doesn't apply to me because I'm in DC conductors anyway. But if I was just drilling through the side of a metal building with my AC conductors, there may be certain ways you have to group your conductors. Generally speaking, you have to group them together, and there may be spacing requirements up to a couple inches depending on your power level to dissipate any heat from induction into that piece of metal. The spread of fire or products of combustion around electrical penetrations or through firewalls, partitions, or floors shall be fire stopped using approved methods to maintain the fire resistant rating. So, you know, if you're penetrating through a firewall, you may need to put additional seals around that conduit to maintain your firewall. Wiring and ducts not used for air handling in other spaces. So there's certain requirements on putting wiring within ductwork. Then we start seeing code introduce us to wire sizes and wire types. And this is where, if you haven't worked in construction before, you kind of start to get overwhelmed with all the different cable selections. Like, you know, what's RHH versus RHW or THH versus THW? It's almost like you're studying, I don't know, college biology or something with gene variants. Well, what we see is there's certain wire rated for dry locations. That's pretty much all wire. And then there's wire that's rated for damp locations and wire that's rated for wet locations. And for the most part, the wire that's rated for wet locations is the same as wire that's rated for damp locations. But actually, you see this N here, this THHN, then there's a WN. But see, so what we can see is not all cables that are listed for damp locations are listed for wet locations. And that might be the difference between a conductor having a little bit of paper inside it or not. You know, the paper absorbing the water and somehow preventing water, if you don't have that absorbent nature, water that gets inside the cable. It's almost like getting an air bubble in a vinyl sticker. It just doesn't come out, and it can actually work its way all the way up the cable and get it into your equipment and short it out. And that might be like if you have exposed cables on the rooftop or on a ground mount and you get a torrential rain overnight and that leaves puddles on the ground or snowfall on the roof, and your connectors are just hanging out in the puddle or hanging out in the snowfall. You know, if water gets into them, it can wick up the inside of the cable. In a wet location, you may get some cable that is resistant to that. That still doesn't mean it's waterproof. You know, that still doesn't mean you should go soak your cable in a puddle because, you know, it's not intended to be submerged. Sunlight resistance is a requirement for solar cable, corrosive environments if you have it, such as battery rooms, and you can only parallel your wire runs for wire sizes that are 1/0 or larger. So, you know, you might have a whole bunch of 3/4 inch EMT conduit on hand that you want to use and a bunch of number 10 solar cable. And so you might say, well, I need to use number 4 cable, but I'm going to use a whole bunch of number 10 instead. You're not allowed to do that. You're only allowed to connect in parallel on cable sizes that are 1/0 and larger, which is when you're getting into like 100 amp service or larger. When you do go into parallel raceways, so you decide to split one cable run into two. The two raceways have to be the same. You know, they have to be symmetrical. They have to have, you know, the neutral is split, the ground is split, the conductors are split, and then they still have to abide by the minimum requirements of the previous sections of code, such as, you know, having a number 6 bare copper minimum for being able to run exposed up to the rooftop, if not if protected from damage, like protected if not in an exposed location. And then we also get some ratings that say, hey, if you're basing these calculations off the tables in this book, you're kind of doing it the wrong way. We're basing these calculations off of engineering calculators and then applying a fudge factor to generate these charts so that they're within the margin of safety. And then we're disclaiming all liability from doing that. So if you run an engineering calculation, you may find that you're doing a calculation for a certain number of amps, and the engineer may come back and say, yeah, we're not getting it, we're never going to get anywhere near that. So let's do the wire sizing off my stamped sealed engineering calculations. There are parts of code that will allow you to go to an engineering calc instead of the tables, and that might give you a little bit more design flexibility. We're being able to undersize your wire for short wire runs between parts. The cost of that engineered stamp on utility scale projects may be less than the cost savings that going from, I don't know, 500 kcmil down to 350 and then doing 2 parallel runs of 250 instead of a run of 500 might be a little easier. Temperature limitation of conductors. Just remember, heat is generated by ambient temperature, also by internal resistance, and then also the insulation too. You know, a conductor with a thicker jacket may not dissipate heat as much. Ampacity adjustment is applied to the conductor using the temperature rating of the conductor if the adjusted ampacity does not exceed the ampacity for the temperature rating of the termination. Okay, what does that mean? So we have a temperature rating of the terminal, and that might be 75C. And then we have a ampacity at that terminal, and if the adjusted ampacity of temperature adjusted of your rooftop conductors, maybe you have a 75C terminal inside the roof, if that ampacity is less than the ampacity rating of the terminal at 75C, then you're in the clear. But if you do your 90C ampacity adjustment ratings and you find out that that ampacity is higher than the 75C allowable ampacity of the terminal, then you have to go back and do your 90C calculations at 75C, and that'll result in you upsizing your cable. A lot of design errors are going to be fixed by you calculating the minimum wire size possible and then upticking it a couple of sizes. what I will often do with my design work is start with the equipment spec sheet and say, well, what's the largest cable size that this equipment can possibly accept? And I work my way backwards. And I say, okay, it can go all the way up to number 8. Well, we're going to have some number 10 on site, so I'll start with number 10. And then if it turns out in my calculations I only need number 14, something smaller, no big deal. I'm still just using number 10, moving with it. Conductors with temperature ratings higher than specified for termination shall be permitted to use for ampacity adjustment, correction, or both. Again, provided that calculated adjusted ampacity does not exceed the ampacity rating of the terminals that have the lower temperature rating. So you have a ampacity calculation to be performed on the wire itself, and then you have an ampacity calculation that needs to be performed at the terminal itself. So how do we actually go and implement this into a solar design project? Well, we saw yesterday that was essentially just going into, and you can take your pick of solar design software. I think Solar Design Tool is ahead of the game when it comes to residential code reports, and they do a free trial. So that's why I chose them to illustrate that. But you go do a National Electric Code report and it'll walk you through the solar specific calcs. What do the temperature derate factors look like for conductors? So here we have a chart. It's a famous chart in National Electric Code. So I'll take out my laser pointer. Article 310.15, ampacities for conductors rated up to 2000 volts with ambient temperatures based on 86 degrees Fahrenheit. So the way that I would get my temperature adjustment factor is I'd say, okay, I'm using 90C cable, and my ambient temperature is not 86 degrees Fahrenheit. It's actually gets up to 120 to 130, and so I need a 0.76 derate factor instead. Well, actually, this doesn't even work all that well because maybe my ambient up on the rooftop is going to get even hotter than that. So I'm going to go and do my temperature correction factors at 104 degrees. And then I'm going to say, okay, well, the rooftop temperature could get all the way up to 150 or 160 degrees. And so I'm going to go with a 90C. And because I'm really overstepping my bounds here, I'm going to do a 0.63 derate. Now, ambient in say Texas is really going to be more, the inspector is just going to look at your ambient daytime temperature. I think it's always good to oversize, and I'm basing it off the ambient temperature of the rooftop, not necessarily the ambient temperature of the wall, because these two, in code in this section 300, this is a general requirement. This is not, is this a roof mounted piece of equipment, or is it a wall mounted piece of equipment? Is it a transformer that's in a parking lot or on the lawn, or is it a solar module that's black and up on the rooftop? Now that's where you would get the engineer out to do an engineered calculation. All these tables are based on assumptions. So your inspector may only look at your average typical high in the summertime for this, but that doesn't mean you can't hold yourself to a harsher requirement. And so then we take the temperature correction factor and we multiply it by our ambient and get a new rating, which is similar to the engineered calculation that's provided here. So they provide they provide a way, a calculation for it, or you can use the correction factors. then there's other adjustments to be made. You know, those cables inside that conduit, they say if you have more than 3 current carrying conductors in a raceway, you have to apply additional D rates. Now, there's some exceptions to that. The first is the raceway has to be larger than 24 inches. And so if I have a protective PVC sleeve protecting my ground rod and acorn, is that a raceway? You know, it's not if it's under 24 inches. If I have a junction box on the roof and I have conduit coming out of the junction box into the attic, and my junction box is mounted 1 foot beneath the roof deck, is that conduit a raceway? I mean, you could argue to the inspector that the raceways should be larger than 24 inches for the purposes of this temperature derate factor. So if you're just shoving, you know, all of your conductors into a protective sleeve before they go through a barrier, that's protection. That's not putting your conductors into a raceway. But if it's a long enough protective sleeve, that heat is going to be trapped in that sleeve, and that's when it becomes a raceway, and you need to allow for that heat to be in there so you don't burn up your wiring. So some of the temperature correction factors do not apply when you're just sheltering the cables. These are for true, you know, then that's pretty common up on a commercial flat rooftop. It's not applicable to, you know, when you're sheltering the conductors that are going into the ground or leaving the trench. You know, they're assuming that if that is getting hot, then the ground is going to work as a heat sink for that. Not applicable to certain cables, so there are additional factors. And then we get into a pretty substantial change of code for National Electric Code, which has to do with derating cables for sunlights on rooftops. What we saw on Solar Design Tool yesterday, and what's common, is NEC 2014, which actually specifies temperature deratings for between 0.5 inch and then 1/2 inch to 1/4 inch and 1/4 inch, you know, to 1 inch and 1 inch to 1.5 inches and above 3 inches, and kind of gave you a gradient. Now the solar industry has been around the block a bit. You know, the data from the industry is saying, look, there's not much difference between a conduit that's right on top of the roof deck and one that's just hovering 1/2 inch above the roof deck. And so they've changed it up yet again. If your conduit is less than 7/8 spacing from the roof to the bottom of the raceway, you have a 60-degree Fahrenheit temperature adder added to your correction. And you don't have that adder if your wires and conduit are 1 inch above the roof deck. So what code is now trying to do is encourage installers to either stay at least 1 inch, you know, 7/8 inch to be technically correct, above the roof deck, or to add an additional 60 degrees Fahrenheit to your temperature correction factor. Or you could use XHHW2 insulated conductors, which are, I would imagine if we opened up the spec sheet, we would find that XHHW2 is solar cable or is super industrial and strong, you know, with a great insulated jacket to keep out the heat in this example from getting into the conductor. So for more than 3 current carrying conductors in a raceway, if we have 4 to 6, there's an 80% D rate. 10 to 20 something, there's a 50% D rate, and then over 41, there's a 35% D rate. So the more conductors we cram into our raceway, the more we have to D rate our modules for heat. And so then we have our allowable ampacities of insulated conductors rated 60 to 90 C up to 140 to 194 F, not more than 3 current carrying conductors in a raceway. So we have our ambient temperature. We've added 60 degrees Fahrenheit. There's not more than 3 in a raceway. And we finally get to the size of our conductors. Let's say we're using number 10, and then we're using the robust XHHW2 wire or solar cable or USC2 wire. You know, what we're seeing is our conductors are rated for 40 amps. If we had those conductors be in free air, you know, we had this chart is exactly the same. This is for the conductors in a raceway. If they were in free air, our number 10 cable would be rated for 55 amps. So you might go and see a chart after a chart after a chart where it seems like a lot of repeat content. Here's not more than 3 current carrying conductors in a raceway, but based off 104F instead of 140 to 94F. So now we see our number 10 at the lower temperature rating. Yeah, the depending on, I don't even know what this part is, the temperature rating of the copper conductor. So 60C, 75C, 90C. I think I was going with 150. I don't know, I guess I'm a little lost here. But you know, what I'm trying to point out is there's a lot of repeated charts where the only difference might be, is this a temperature calculation for a raceway, or is it for free air, or is it for a messenger cable, or for bare covered, or for you know, a direct burial wire run. Okay, so where are we at? We've talked enough about the neutral wire. Oh, I guess the question is, so does the neutral then count as a current carrying wire? Because what the neutral does is takes any unbalanced current. So if you have 5 amps on one side of one leg of the split phase and then 7 on the other, the amperage in the neutral will be 2 amps. And it's not required to be counted when you have more, you know, 3 or less. When you're counting the conductors for current carrying, the neutral does not count. Unless you are getting into commercial circuits with non-linear loads. So on commercial circuits, you may count the neutral wire at that point, because when you have non-linear loads, you're always going to have some current in the neutral wire, whereas on split phase, it'll be going down to 0 at times. So here we have a delta service, a Y service, and in these, the neutral wire will be counted as a current carrying conductor, but in the residential service, it would not. Let's see, for services rated 100 to 400 amps, the service conductor shall be permitted to have an ampacity of not less than the 83% of the service rating. You know, actually what we're seeing is that the service conductors get a little bit less of get a little bit more flexibility, you know, more exact sizing, because those service conductors are being protected by that main overcurrent protective device of 200 amps, and they're not going to feed more than 200 amps. So if they get overloaded, that main breaker is going to switch. They don't have to worry about multiple conductors being, you know, the effects of temperature and what have you so much. Let's see here. Grounded conductors shall be permitted to be sized smaller than ungrounded conductors for feeder as feeder conductors if certain conditions are met. Let's just And then we have engineering calculations to say that conductor ampacities can be calculated per engineering, and voltage can be calculated as well. So let's see, we have specifications when you are laying conduit into ductwork or burying cable into a trench on how those cables should be laid out with minimum clearance requirements. On utility scale arrays, if you're opting for direct burial, you may be putting in your power lines and then realizing, oh, well, the fiber optic guys want to go into the same trench. And so you might have to plan 24 inches of spacing between the power lines and the fiber optics to avoid electrical interference. Getting into our cable types, there's a section of code that will actually start breaking out what all of these mean. So here we have RHW versus THWN versus XHWN2. And what we see on all of these is they have this 90°C temperature rating. And then we have different damp dry versus damp and wet versus wet versus wet. So all of these with a 2 on them refer to a wet environment. And if it doesn't have a 2, it's not in a wet environment. So solar cable, the cable that's up on your rooftop, it'll be like a USE2 cable or THWN2 cable. Maybe the silicon versus thermoplastic refers to perhaps the R versus the T or X. But you can look it up in code. So then we get into philosophies of, well, how much cable can we actually put into a conduit before it's considered too hot or before it's considered full? And furthermore, when we do work inside a box, how much can we fill the box up? And that's the kind of knowledge that a general electrical contractor is going to have, but a solar guy is not. You know, a solar guy might be trying to squeeze it all in and just close the lid, almost like a middle school slob's locker, you know, just pushing it in all in. But there are rules about not just conduit fill, but box fill. And so the general rule of thumb is don't exceed more than 40% of the cross section. And now if you're doing splices and taps and terminal blocks and filling up the box, like maybe just with one particular cross section, like a mounting board on the back of a box for your terminal connectors, that should not exceed more than 75% of any individual cross section of the box. And so you might get into a debate with your inspector. Well, I have a service panel monitor that goes inside my electric service panel, and there's enough space in the panel for me just to tuck it down into the corner. You know, what he might say is, well, the service panel has a 2-inch gap, and that monitoring equipment is at 1 inch and 7/8, and the lid just barely fits on top of the monitoring equipment. You know, that would have to be 1.5 inches for it to be 75% of the cross section. That said, if it does fit, the inspector might say, well, I don't really like you putting equipment into my service panel. Can't you do a panel outside of it? And you would say, well, you know, actually, it meets the cross-sectional fill requirements of the service panel, so I've addressed code in it, and I don't want to bring cables unnecessarily out of the service panel. I'd rather just keep it in and see what he has to say to that. Okay, let's see. You know, there's for room layouts, doors. Here's one that can get you for wire bending. You know, I look at a piece of EMT and I look at a conduit bender and I look at these electricians with big arms who brag about how they can bend any conduit anywhere. But then you start running up against the physical limits, like, you know, only being able to fold a sheet of paper in half no more than like 7 times, maybe 8 with a machine. You get to the point where you can't do anything anymore. And so on this off-grid home where we put came into the roof cap, we only had a couple of inches from the roof cap to the gap in the top of the roof for us to make our bend. And because we were in a wet location, we wanted a liquid tight metal flex conduit. DC conduit must be contained in metal. So we needed a metal conduit. We needed it to be grounded to the Z-purlin, grounded to the rooftop. We needed it to have a radius bend that was short enough. And so we can go and see for some of these wire sizing, when you get into larger cables, you know, sometimes you have to allocate feet in order to bend the cable enough for it to go where you want it to go. Let's see. So there's a maximum size of the maximum number of conductors and conductor sizing to go into a junction box. You know, as a solar installer, I just learned the conduit fill. And so when I get to my junction box selection, I'd kind of eyeball it and say, oh, all of that can fit into a 12 by 12 junction box. And then I noticed that, you know, we were really installing and buying whenever the electrician would go out, you know, an 18-inch, my 18-inch junction box. I said, well, can't we get it something smaller? And he goes, no, you have a box fill requirement in electric code, and, you know, you have 3 circuits of modules, and so I have, you know, I have 6 number 10 AWGs plus a number 6 from my ground, and so I can't use a small box. I have to go get a larger box instead. Volume allowances for the boxes. And so you get into ideas that, like, well, okay, so here I have an LB and this says small conduit bodies. So not something that's a gutter, not something that's a box, but this kind of attachment, it does have a lid. So you could think, well, can I sneak a splice into here and take the lid off and put the lid back on? Well, there's a provision that says on small conduit bodies, you're not allowed to splice inside the lid. So what this lid is for is so that when you're pulling your wire through it, you can take the wire all the way out and then push it all the way back in and continue on with your wire pull. So, you know, you go more than 3 bends on a wire pull, you get to that 4th bend, and then you have a knot, and your wire becomes really impossible to pull. So you have these little breaks in your conduit so you can come out and then go back in. Still not intended to be serviceable. And so we get into box depth, where conductors of 8, 6, and 4 shall have an internal depth of not less than 2 1/16, whereas conductors 10 and 12 is not less than 1 3/16. And you think, well, how would this rule and section 314 impact solar design, you know, sections on down the road? Well, if you want to hide the roof-mounted boxes underneath the solar array, you got to realize that there's only going to be, you know, you might want 1-inch clearance from the roof so that you avoid the temperature degradation requirement. And so your box bottom is 1 inch off the roof, while your attachment points are only elevating the rack about 1 inch off the roof. And then your rack may be 1.5 inches tall, and then your module might be 3/4 of an inch tall. So you only really have 1 3/4 inch of space to deal with for your box size on the rooftop. So if you're going into number 8, your box size may be at least 2 1/16 inch. That's too large to fit underneath the solar array. So then it becomes down, well, what is the largest cable size you can install on the rooftop so that you can still hide the conductors underneath the array, but have code compliant boxes that are nice and tight and compact, but still have the largest cable size for voltage drop and resistance. And lo and behold, we get to this number 10 AWG, and it should be no surprise that number 10 AWG is like the most common solar cable size up on a rooftop.